Maybe I get started. Good morning, everyone. Today we have Professor Bingming Li, who's an associate professor in the Department of Manufacturing Systems Engineering and Management Science at California State University, Northridge. He's the director of Laboratory for Sustainable and Additive Manufacturing. He works on 3D bioprinting, 3D metal printing. He has more than 40 papers. He's garnered many grants and awards from DoD, NSF, DOE, Clean Energy, Smart Manufacturing. And also he received the Outstanding Engineering Achievement Merit Award from the San Fernando Valley Engineers Council. He'll tell us about additively manufactured titanium scaffolds with cell applications. Professor Lee, please go ahead.
Okay, thank you, Mami. Hi, good morning, everyone. It's my great honor to make the presentation today for the Terasaki Institute for Biomedical Innovation. Sorry. So today my topic will be the additively manufactured porous titanium scaffold, the cell proliferation. So here's my background. I got my bachelor and master degree in mechanical engineering, PhD in the industrial engineering from Texas Tech, and then got a 1 year postdoctorate at the University of Wisconsin. So I joined the CSUN Cal State Northridge in 2014. So during this summer, I just promoted to the associate professor. So here's some other, my professional appointment. So it's my great honor to join the Terasaki Institute for Biomedical Innovation in last month. As an affiliate faculty, I'm so exciting, to work with all this group. And I'm also the faculty lead in the manufacturing for NASA Autonomy Research Center for STEAM, and the faculty mentor for the US Department of Education AIM Squares since 2016, and also the NIH Biopolder Infrastructure leading the Biopolder program since 2015. So you can see these two, the DOE Department of Education and NIH Biopolder is for training and research for the under and the graduate students overseas. And so one is $40 million grants for 10 years. Another one is 12 million for also for 10 years. We renewed once. And here are some of the some funded project I have received. For external grant, totally I received like 9. And then like either PI or co-PI. As PI, I receive like around $800,000. Most of them is from DoD, SF, and the DOE SESME. So right now, currently, I'm working on the 3 active grants, 1 SF and 2 DOE grant. And here are some internal grants I received at CSUN. Most of them is for research and also to support the students. For the research, I will introduce them later. My area is 3D bioprinting. So in 2015, I got the major, support from the university to establish my lab in the 3D bioprinting. So here's the research interest, all the research areas for my lab. My lab is the Laboratory for Sustainable and Additive Manufacturing. So of course, the first area is additive manufacturing. I focus on, our lab focus on the 3D bioprinting, the metal 3D printing, and we also do some work in the SLA, FDM, and the jetting. And right now we're also working on the smart manufacturing, like a digital twin, the smart kinetic worker. So these are the 2 new areas we worked since 2 years ago for the DOE SESME grant. And when I was a master on the PhD student, I have been working on a long time on the sustainable design and the manufacturing, like a green design, manufacturing energy efficiency, the life cycle assessment, the sustainability analysis, and even earlier. And then we also work on the recycling, remanufacturing. But now my research is more focused on the 3D bioprinting, metal 3D printing, and the digital twin, and the smart kinetic worker. These are some of the facilities. Just give you a brief introduction of our lab. So these are the three 3D bioprinters we developed by our own. Like this is the one, the major component we purchased from Microfab in Texas. This is a PH46. It's for fluid inkjetting 3D bioprinting system. And then we develop the whole system, integrate some major component from this company, and then develop our own. And then this is the second one we developed by for our research is a DLP, the digital light projection 3D bioprinting system. And then the last one is the three-head micro extrusion 3D bioprinting system we're using now for our lab. And here's some of the facility. I think you are the experts in the biomedical and biology area. I think these are just the normal equipment for cell culture. But for me, for our lab, it's a the good milestone for us because our background is in the mechanical engineer or the industrial engineer, right? We're in the traditional area, but now we are able to establish our cell culture lab, and then we can do the cell related, the research. That's really good for us. And then here's the regular 3D printer. This is the one for AM400. This is the metal 3D printer funded by the DoD almost 3 years ago, but unfortunately, we were unable to install on campus. So, but the good news is these 3D bioprinters will be moved to Terasaki Institute. I think this week, maybe on Friday. So I'm so excited to work with this outstanding institute in the biomedical area, so we can work on the metal 3D printing and the 3D bioprinting for long-term collaboration. And these some other 3D bioprinters, sorry, the regular 3D printers in my lab, like the Stratasys, the Dimension U-Print, and the Formlabs Form 2, and then the Thermojets. These are just the desktop 3D printers we have. So now I'm going to go over one most recent project we conducted last year, and then I will go over some other small project we have done before in the 3D bioprinting area. So the first one is the Porous titanium scaffold. I think I assume you are familiar with the bone tissue structure, right? So they have these all the different structures, and then you can see these projects we're trying to mimic the parts structure for the bone tissue. And here you can see these are the parameters, for the bone tissue. And then for us, our focus is on the microstructure of the bone tissue, and then trying to mimic and generate the different geometry. And then we are going to use the metal 3D printing to fabricate the tissue scaffold and then put the cells inside to monitor the cells. So here you can see for the bone structure, typically there's unidirectional, typically between the 0 and the 180 degree with the changing angle of like 7.5, right? This typically there will be between the 8 and the 82 degrees. That will be ideal, for the collision orientation. And here is some of the more details about the porosity generation. Right here, this is the compact in the bone tissue, and then this is the spongy. And here will be the laminate. So it's the different layer of the laminate. So we're trying to use the, CAD tool, the computer aided design tool, to mimic the structure. So our design methodology allows for the creation of the structure with the multiple prostates similar to the human bone. So before the emergence of the advanced manufacturing technology such as the 3D printing, right? I think typically the process scaffold were manufactured using like a fiber bonding, the molding, the foaming, these different biofabrication method. But now since the 3D printing is the new technology, and then we're working on this area, and then we found, okay, we can use the 3D printing as the alternative method, right, to figure out the feasibilities, and then to invest it on the different structures, and then the affections on the uh, biomedical area. So based on we have the researchers previously, based on the literature review, researchers have different opinions on the relationship between like a scaffold pore ways and their salvability. So, but these projects, our objectives to explore the relationship between the pore size, the shape, and the mechanical property of different additively manufactured parts titanium scaffold. And also in the meanwhile, we will examine or invest their cell availability for cell ingrowth. And here's now the method we're using and also the tools. So the this was done by one of my master students. His background is in the architecture. And because for our engineer, typically we use SolidWorks, so we use Autodesk Inventor or CATIA as tool. And then he used Rhinos. Rhino is just a typical 3D uh, modeling software for architects. And in this, the advantage of this software is they have the Grasshopper. This is the visual programming, the algorithm modeling plugin for the Rhinos. And then they also have the Interlattice. And Interlattice is the open source plugin for the Grasshopper. So we use this for creating the solid lattice structure inside the model. And then this software, they give us the capabilities to find the optimal balance between the porosities, mechanical behaviors. So we initially we pick up like around 10 different geometries and different units. And also we print them out, but later on we found these four would be more effective. So these four, the different the structure we call it a built-in cell, and in the intralattice we use to generate the scaffold, and then the size of each cell is adjustable, so we can adjust it from X, Y, and Z directions. And here is the grasshopper, right? The algorithm, based on each small unit cell, and then they will be using to generate the 3D geometry. So here you can see this is the render's view for, here's the Rhino's 3D model. And here this is the unit cell in the interlattice. So for each one, these three parameters, they can adjust the cell size in the X, Y, and Z direction. And this module determines the overall frame for the boundaries. In this case, there will be the box, right? And then this is the number 6. So here is the radius of the struts. And number 5, here's the module determine the type of the mesh. So eventually they can generate these different geometry. The number 1 is just the cell module, and these 3 different parameters, right? The number 3 is the 3 different parameters determine the number of cells and modules in each direction. And number 4 is the module determining the overall frame. So here's the 3 different sides. We invested on the different literature reviews, and then based on the different studies they have done before, and then we found the effective porosity. I think it's from 200 to 900 uh, microns. And then here we just choose the 300, 400, 500 at these three basic parameters for the pore size. And we adjust the different parameters, for diamond, the honeycomb 1, honeycomb 2, and the last one is the grade. So these four different uh, the cell structure, and then these are the three different pore size. So and then we generate 5 by 5 by 5 millimeter cube. So this is our final, the scaffold size. And because a human bone is made of different porosities, so have this software, we give the ability to generate the different pore sizes to design a scaffold. They have a similar mechanical and geometrical property of the human bone. So we eventually we focus on these 12 different scaffold, right, with different pore size and the different geometry, like diamond, honeycomb 1, honeycomb 2, and the gray. So this is the different one. And for each one, they will have different size. So eventually we'll have 12. But in the metal 3D printing, we prepared more than, I think, 10 different cell structures. And then I think the other 6, some of them is either failed, I will show you in the result later, or it's not effective. So eventually we only use these, pick up these 4 of them for the later research for the cell proliferation. So here's the scaffold conform to the bone geometry. We also design these different, the shape of the structure as well. Like here's the pore size, and this is a single cell, and then we generate the semi cylinder, to mimic this the bone structure. And we use here is the formula we use to calculate the porosity for each geometry we have. And then here's these 4 different structures. We make sure the smallest distance match the pore size desired, because different shape, they have the different geometrical performance. So we just use the smallest distance for each structure. So here you can see we used the concept laser M2. This was printed by my partner. It's the Cassian company in the Southern Oaks. They used the concept laser M2 to print out all these. You can see these more than 10 different the structures or the geometries on this 10 by 10 inches by 10 inches build plate. So we print all over, I think it's almost 100 different samples. And the cube, this is not a small cube, 5 by 5 cube. This is not to mimic the small bone structure, and then here, the first one is we just use the microscope. We review the pore enlargement of the proxy like 20% compared to the original CAD model. And you can see here, some of these models, they failed, right? These, they failed. This one, they also failed for the metal 3D printing. So eventually we only pick up these 4 out of these 10 different geometry, for the further investment. And this is the SEM image. We are trying to figure out what's the internal structures, right, after the metal 3D printing. Because the metal 3D printing, let me go back to here. This one, the parameter for this metal 3D printings, the metal powder we use is the titanium Ti64. And then the layer thickness we use is a 14 micron for each layer. And of course, this metal 3D printer, the resolution can go from between 20 micron up to 90 micron. But after we consult with the professional, and then eventually we just pick 14 micron as the layer thickness. And because the the features of the metal 3D printing. Some of them, like over here, they shows in these slides, right? Some of the, you can see a lot of the metal 3D printing itself, they just melt or the sinter the metal powders and then combine them together. They use laser. Laser is they use a 400 watts laser, right, to melt these metal powders like stainless steel, the copper, nickel, and titanium. So the high energy laser will, the melt or the sinter the metal powder and then combine them together. So here inside of the metal powder, right, you can see it's not perfect shape either in the rectangle or in the circle, right? Even we design that in that shape. But for this is for the bone structure. I think this is fine. But for mechanical parts, right, we have to make sure they have a really good finish surface. But this is for the bone because eventually the cells will grow inside of the scaffold, and then these structures, I mean, the rough surface will help the cells to grow as well. So this is good. I think this is good for the bone implant. And but here you can see the some of the percentage, the missing. So here you can see some of these missing, pieces over here, and some of them is like either missing pieces or the slight distortion. Like here, some of the distortion. This is the shape is not as perfect as the one we designed in the CAD model, right? Because the metal 3D printing itself, for each layer, they have like 40 micron. And then they will, they only build, after the slicing, they will lose some information. And for the printing, they only print like one layer by layer, right? Like they can only get the accurate information on each layer. And then next layer, that will be different. They will miss some information between these layers, like 40 micron. So that's the reason for some missing pieces and slight distortion. And after the printing, we pick up these 12 samples for the compression test. We use this testing machine, and then here we showed, the human bone, typically they have a high compressive stress is 170 megpa. And out of these 12 samples, we just tested them because for each sample we have 4. For each same unit we have 4, and then we just use one of them for the compression test, and the other 3 for the later, cell viability investigation. So here you can see all the 3 diamond scaffold they filled. These 3 diamonds, 300, 400 micron, and 500 micron. And then the compressive stress is 37, 37, 68. So it's much less than the 170 bone, human bone scaffold. And but for here, this the honeycomb 1 and the honeycomb 2, I think they have a good performance. Like they have a high compressive strength for this. And later on, after the compression test, then we pick up another 3 cells. For each of them, we use the cell culture and fix. So this is the procedure for our cell culture and fix. And then we trying to figure out whether the cell they can survive in this scaffold. I think that this process is more familiar for you because we are from engineering background, so we collaborate with the one professor, Jonathan Kelber, in the biology department at CSUN. So they help us a lot, for this cell culture and the fix, and then for the later the investment. So here's the seeding scaffold. After that we put the cells inside, and then we change the medium every 3 days. And for here the cell counting in the 1 milliliter, and so these are some of the SEM results we got after 30 days of the culture. And then you can see here, this is an A, and here the A, B, and C, this honeycomb 2, the 300, 400, 500, right? This shows the highest cell proliferation, about like 86%, like A from this one, A and D and E. So this is honeycomb 2, because the D and the E is the actual image, same as the honeycomb 2, 300 micron. The B and the C is 400 and 500. And this honeycomb 1, the grade and the diamond is because they filled in the compressions test. So this one, but we still put the cells inside and look at the structure. But eventually we found maybe the honeycomb 2, 300 shown maybe it's the most effective one. But this one is I discussed with our the partners in the biology, right? Since this is only a couple layers for the cells, and for further discussion, we need to put more cells for the 3D cell culture, and then to investigate whether the cells they can survive and grow into the tissue inside of the sponges, right? The inside of the bone scaffold. So I think this one we will continue to work and then investigate on the more influence on the like a different geometries of the scaffold, and then different porosity size, pore size, for the scaffold. So that's our preliminary, the result. And here we also did the 3D bioprinting for the neurosim, the blood vessel, like, I think the 3 years ago. This is a small project we done. Here's, I think, the challenge for cardiovascular, disease. And if any of these blood source was blocked, and then they will like the blockage, right? And then they will result in the disease. So we have to make sure they have a better blood vessels, and then over here. So here they will generate like a dead muscle tissue. This is the first version of our 3D bioprinters. Right now, they have a second version of the 3D bioprinter. So this is the one only with one head. So this a neural model is a complex structure due to the bulge created on the artery. So this work that we're trying to use the micro extrusion method by using the bioprinter was developed in our lab. And this is we developed the 2 different syringe, and then for our investment. So here's the preparation of our bio ink. This bio ink typically is based on the sodium alginate dissolved, and then we prepare different concentrations, and we check the viscosities. And here's the new, we use the 2 different methods. This is the one, the XYZ stage we developed for our 3D bioprinters. And then this is the method we use, the mold method. And then here is the fresh print by the alginate in the red dye for the visualization purpose. So here's the preparation of our support baths and ink, which is used, typically is used sodium alginate. And then the solution here we use like a mason jar, and then remaining space jar will be filled with the CL2 solution. And we also use the centrifuge process as well. So you can see here is for different 1 or 2 hour at least, and then eventually we can fabricate this this process, these small samples. And we also collab with the professor from mechanical engineer. He's the expert in the fluid dynamics area. So we check the fluid dynamic testing setup for this small segment. We fabricate a 10 millimeter segment of the blood vessel, and then trying to test whether this 3D biofabricated the blood vessel, they will have the same mechanical property, like the fluid dynamics property, as the the human blood vessel. So here's some of the preliminary results. We can see this average of the image taken at the mid-plane locations and showing from image A. Here the flow is going from right to left at the Reynolds number of 50. So the average of the image taken in this location show the complex structure forming near the neck in the open of the sac. And then figure B here, they're showing the preliminary measurements for the flexible model, showing the impinging velocity at the left side of the necking region. And then for C and D, the several flexible tube model was tested for the PIV measurements, and then the sample image is showing over there. So, however, these preliminary measurements show the light from the laser is diffused in the tube. So this is for the CCD, camera. And this is another 3D bioprinter I showed in the beginning of this presentation. It's an inkjetting based 3D printing system. So for this one, we initially we focus on the droplet formation, right? We investigate a relationship between all the different parameters and influence on the droplet formation, because this is the DOD, drop on demand technology for the inkjetting system. And here's just, this is the schematics of the vertical printing configuration. Here's the horizontal printing configuration. And these are the inkjetting droplet formation setup we invested on the on the sodium alginate based hydrogel. So here's the control values, the echo time, dwell time, the rise time, or these are the voltage, frequency, right? And then parameters we vary. The varies like a raise fall times, voltage, the echo time, the bio-ink concentration. For the concentration, we prepare these 5 different concentrations for the testing. And here's the piezoelectronic inkjetting nozzle setup, right? Here is the LED scope, and then this is the piezoelectric nozzle. They can activate or the trigger, the surface, and then they will release 1 drop late per time. So it's we call the DOD, the drop on demand. And then our goal is to form this perfect, this is the prime, the droplet, here is the ligament. So we're trying to get the perfect, the droplet formation, because some of them you can see they will have lagging over here, or it's not, it's continuous, right? We have to control these parameters that eventually get this 1 droplet per time. So we use these samples, and then for different different concentration of the samples, like these 5 different concentrations, and then these 7 different times, and then voltage is we pick these 5 different voltage, and then this is 4 different raise and fall times. Here's the we trying to effect all these 3 different effects due to here is due to the change in the rise fall times. Here's due to the change to the applied voltage. Here's due to the change in the echo time, the dwell time. Right, through the experimentation, it was found that all the bio-inks tested, they have the good extrudability, with exception of like 1.25% of sodium alginate. So a time dependency was determined in these studies, but the longer the hydrogel was exposed to the air at the orifice of the micro nozzle, the more the hydrogel began to swell. And through the various studies that were determined that the hydrogel with high water concentration swell when exposed to the air. So this one is still under the investigation for further discussion, then for further the studies of different the mechanical properties on the 3D bioprinting in terms of the inkjetting technology. And is some the samples, so we print them out, like inkjetting printed cell culture structures, simple structures. And this is another project we did 2 years ago. It's a small project for the students, a group of students work together, use the Autodesk Remake to utilize the import the proper file format. You know, we got the file from UCLA. They got the CT scanning of these mandible structures, and then we convert this the CT scanning file, you know, to the STL, and then converting this STL file to the proper like Fusion 360. We use Autodesk 360, and then to generate a cylinder-shaped T spline with 9 subdivisions to mold the CT scan screen mold. And then the figure 2 is showing the mandible implant region. And later on, we use the Formlabs Form 2, the resin, you know, 3D printing for the SLA for the resins. And then we just use this 3D printer to print out these samples. This is the implant mockup. So this one was just a small project we did. So, but the model was printing with 100 micron resolution. All features were printed properly, and no anomaly was found from this sample. I think that's all the, you know, the brief introductions of the, you know, some of the projects we have done before. So I think that's it. That's it for my presentation. Any questions? So I think I'm more than happy to leave maybe 20 minutes for the Q&A section, so we can have more discussions, and then on the you know, the further investment, especially for the collaborations between my lab and then the Terasaki Institute for different projects, because I know you have excellent research in the biomedical area and also in the bioprinting area.
We have one question. It says, what are your printing speed capabilities?
Which one?
For the Renishaw, probably the metal printer, and, you know, in general.
Oh, in general, I think for that one, it depends on the laser scanning speed. So typically, that's the laser scanning speed is one of the parameters to describe the printing speed capacity. I think that's the one. And if you're discussing the like a printing speed for the large products, like the 5x5, let me see.
I think that 3D printing is a little bit slow. I think that's what he's getting at.
Yes,
you know, compared to lithography. How long does it take to print one of those pieces?
Okay, yeah, let me show you. So for this one, if you go back to this slides, yeah, the metal 3D printing is relatively slow, especially for this 3D printers. We have one laser head. So this 10 by 10 inches build plate, this one take I think 13 hours to print all of them. But now, like EOS and the concept laser and the Renishaw, they have new models. They have 4 printing heads in the same time. So the printing speed will be enhanced like 4 times.
Okay.
Yeah. Depends. Yeah.
Couple other questions came in. One of them, why you choose titanium 6 aluminum 4V rather than SS316L? I understand TI-64 has better mechanical properties and probably biocompatibility, but in terms of commercialization, SS316L wouldn't be a better option.
Yeah, this is a pretty good question. Yeah. Actually, in the like a bone implant area, right? In the medical applications, I think there are some discussions or some like you can either use the stainless steel 316L, right? Because this is more cost effective, and then they also have a better the mechanical properties as well. I also saw a lot of researchers, they use the stainless steel 316 as the bone implant. But for us, is we have done some the research on the stainless steel 16 because we use SS16 is the most popular and mature materials for metal 3D printing. So they also the cost itself is much less. Like the metal powder, in terms of metal powder, stainless steel 316 is only like $106 per kilogram. But for titanium is almost $600 per kilogram. So the cost is much higher. But the reason why we pick the titanium 64 is we want to invest on the titanium's biocompatibility, right? And so, yeah, it depends. Like because we print out some samples with the stainless steel, for a lot of mechanical parts, functional parts before. So for these studies, we think, okay, maybe titanium will be, they have a better mechanical properties, and also they have the better biocompatibility, if you for the bone implant, right? So they'll be more safe than the stainless steel. So we just use the titanium for this study. But yeah, I know like a lot of the researchers, they use the stainless steel 16 as well. Thank you.
The second question is there any difference in the porosity of the Honeycomb 2 and Diamond 300? What's the explanation for the difference in proliferation in different scaffold designs? Pore geometry, porosity, integrity.
Yeah, this is another really good question. Thank you. Thank you. Right. I think it's Russell. Yeah, the difference in the porosity of the Honeycomb 2 and the Diamond 300, as I mentioned, this study, from our background, from our labs teams, we have we are not the experts in the like a cell culture and the biomedical, the area. So our, the idea is trying to do some of the studies, initial studies, to figure out what's the relationship between the porosity of the Honeycomb 2 and, all these different things. Like we have this, from this image, you can see we tried 10 different, geometry. And but some of them, for metal 3D printing, because of the feature of the metal biofabrication, right? Some of them field, like here, you can clearly see some of them is field. And then that's why eventually we only pick these 4, Honeycomb 2 and the Diamond 3, Honeycomb 1, and the grade. In terms of the porosity itself, if you go to this slides, and then so I think this one, go back to here. We checked, oh, sorry, I forgot to attach another table. So they're showing the different porosities for these different structure, for different, actually we calculated for the 10 different geometries, but I forgot the data, sorry. If you want, yeah, I can share this data with you, like the porosity for these different. And then what's the explanation for the difference in the different scaffold design, right? For the cell proliferation. This is a good question as well. Like I mentioned here, for this study, you can see here, we only test the, the one layer of the cells, right? To get the better, the cell viabilities. Like I talked with my partners last year, in biological department. I think that would be better to invest on the 3D cell culture. In that case, they will invest in, more details about, because for the porosity is 3D, right? You cannot just verify the cell proliferation on one layer, right? But because here is the porosity, we are talking about the whole porosity, the volume, right, inside of the structure. So for that one, but based on this result, right, here we only show the Honeycomb 2, 300 show the highest cell proliferation, but we, I have the, long discussion with my partners, like later on, maybe the conclusion will be different if we invest on the 3D cell culture to show the cell, whether the cell they can grow into the tissue in these different structures. So yeah, this is a pretty good question. Like, so we're still, the under investigation to do more further, the studies.
So another question is, do your printed scaffolds have mechanical properties like a bone? On the other hand, is it possible to use bioink instead of common materials like titanium for 3D printing of bone?
Yeah, it's Maman, this is a good question as well. Like, I think this is I have saw some publications. They already using the 3D bioprinting. The hydrogel. They just use different hydrogels, different materials. Like they put the nano, different nanoparticles, and then the different materials, and then prepare the hydrogel, and then they can eventually, the grow into the bone structure instead of metal one. Yeah, I saw some really strong results from that area. So they either use injection printing or DLP printing. The also for the micro extrusion technology, they just prepare the hydrogel and then they can grow into the bone tissue. That's another good area. I think a lot of work, the research work has been done or is working on this area.
And what is the advantage of titanium in scaffold use?
Excuse me?
What is the advantage of using titanium for the bone scaffolds?
Oh, I think for this one is for the titanium one. I think the one advantage is the mechanical property. The second one, I think, is about compatibility of the titanium itself, right? This titanium materials has been approved as a really good candidate, for the bone implant in the past, I think like 20 or 30 years. But they just use a different biofabrication method, not the 3D printing. They use the forming, the biobonding, these different methods. So that's why over here we use the titanium.
Is it possible to do multi-layers, hybrid structures, maybe molybdenum, titanium? Have you done any of those?
Yeah, I think this is possible, but I never did I never tried this one. But if you want, yeah, we can try and then to do some investigation. Yeah, exactly.
And one final question is, for the cells, do you treat the surface of the metal beforehand, before seeding the cells?
Oh, we didn't do any mechanical like a polishing process, or we only do the cleaning process. We use the ultrasonic to clean the surface, and then we also use this process here, the cleaning process, and then to clean the surface. But we didn't use any of the mechanical processing like polishing or for the titanium surface. No.
How about putting some proteins, fibronectin or collagen or something?
No, not yet for this study. No, but that's a good question, because I think that we're working on another project. But that one is not for the biomedical application. It's for Harley Davidson. We're working on the Harley Davidson on their motorcycle engine. So they have a really high requirement, for the surface finish. Their requirement is a 6-micron surface finish, and then we use this a magnetic polishing process, electronic magnetic process. And then we put some, nanoparticles and fibers inside of the fluid. So, and then we apply the magnetic field into the internal channel of the oil, the oil channel fluid. So yeah, in that studies, we use these fibers and the nanoparticles inside, then to trying to polish the surface, internal surface, and get like a shining, the surface as like 6 micron to meet their requirement. But for this study, I didn't, because I thought, Yeah, this is a good question. I mean, for the bone implant inside of this structure, right? If we need this polished surface, you know, and then that would be better for the cells to grow or to survive, and then we can do this study. But for this one, we didn't. We just clean and then use ultrasonic to clean the surface. That's it, and then put the cells inside. Yeah, but this is a good question. Like we can discuss later. Like if this is a good topic, and whether the polished surface will be better, or this 3D printing the surface like you see over here, right? This surface you can see is typically is rough surface. It's not the polished surface. Yeah.
Okay, a few more questions came in. Is inkjet printing capable of printing cell encapsulated hydrogel since high stresses would be applied to the droplets at high frequencies due to piezoelectric nozzle, which can diminish cell viability?
Yeah, this is the really good question, but I don't have answer right now because you can see here, inkjetting itself, of course, is capable of printing cell encapsulated, the hydrogel, because we tried before. We put the cells inside of the hydrogels, and then to check the effects or the influence of these cells, because some of the preliminary results showing it's not that reliable. After we put the cells inside of the hydrogel, because before the cells inside, right, and then we adjust all the parameters, and then it's pretty good. But after we put the cells inside, another challenge is how we can make sure each cell was printing out one cell inside of the droplet, and then they can print out. So, and here like a high frequency, yeah, and they also have a concern, but we discussed with my partner. Another challenge is whether this high frequency or the piezoelectric nozzle will, kill the cell as well. But so this is unknown now for me, because we did the investigation, but that one is we didn't get a really promising result showing this relationship. Thank you.
Great. Did you study in the cell adhesion properties in different pore size or different structure? Because TI-64 being FDA approved material at every pore size will show biocompatibility.
Oh yeah, this is excellent. Yeah, this is excellent. The question. Because before we determine all these different pore size, and we also check the FDA, and other studies. Yeah, they also investigate on the like cell adhesions properties in different pore size and different structure. So that's why we want to work on this area. But this is not the focus of our project, but we also consider, yeah, we did consider, like, because they give us a range is from 200 micron to 900 micron, a large range of pore size. Yeah, but eventually we pick up. We also use these different pore size in the 10 different geometries as well, but some of them failed. So eventually we only got these 300 and 400 and 500.
Okay.
Yeah.
Which one is easier to print with higher resolution, 316L or titanium alloy? If 316L, can we print a layer of 316L and coated print with a tiny layer of titanium alloy to improve its mechanical corrosion resistance and biocompatibility?
Yeah, I think this is a good question, excellent question. Like, Mehmet, I think you know the Professor Xiaochun Li, right, from
Yes.
Mechanical and Aerospace Engineer Department. Yeah, he has done a lot of work about the either coating different layer of the. He also put some nanoparticles of titanium inside of like a copper or stainless steel, and then get a high uh, high performance or the alloy? Yeah, this will be a really good question. I think this is also really good topic as well. Like Professor Lee from MAE department, he has done some research on the like aluminum, stainless steel, nickel, and copper. But here, if I don't know the answer, but this is a good question, like whether we can add a coating, like a layer of titanium, right? Coat with the titanium, and then whether we can achieve like higher resolution of 316 stainless steel. In the meanwhile, they have a better biocompatibility. Compatibility. Yeah.
Great, great.
Yeah, but
You know,
I didn't. Yeah, I didn't do that. I tried to collaborate with him and then work on the. But most of our work is on the mechanical property. On the different like aluminum and the copper for the rocket dyne engine. And then for the aluminum is because for some of the aluminum is really hard to fabricate. Like so we just add these nanoparticles to improve the mechanical properties. I think this will be a solution, alternative solution. We can work on this one in like whether we can put some coating right on the layer of the 316.
I see.
Yeah.
Well, we're running about time. Thank you so much for this great talk. We learned a lot about 3D metal printing. Appreciate your help. Look forward to the continuing collaboration.
Yeah, thank you so much. Yeah, I hope we can from this talk we can inspire some ideas and then for the further discussion, and then we can like today like they have really good these questions as well. Like we can keep working on some of this area and the topic and then move forward. So to have a comprehensive investigation on the 3D bioprinting, right? We can also try different metal powders, because previously like this one, this sample, this build plate, right? I paid almost $4,000, for this company to print out these samples. Yeah. So the metal 3D printing is not the cheap. It's expensive and it's also time consuming. Yeah. But I believe like with this technology revolution, then we will have better solution like a high speed and then higher quality for the biomedical, the application. Because right now, like Renishaw and the EOS from Germany and constantly they have developed the 4 laser heads, so they can print out, they can in the same time. For this one, the machine is only 1 print head. Yeah.
I see. Great. Thank you so much.
Thank you. Thank you so much. I really appreciate it.
Yeah. This concludes the talk. Thank you. Bye-bye.
Okay. Thank you.